Hi Tony. Um, Today we see what is the geometric series. In the last class, I talked very briefly about it. Today we go into the details of that series. Geometric series. As I said earlier, there will be an initial term will be there, like a initial constant, anything like a, and a particular constant. What is that? A constant number is multiplied in every single step. So, like if a is multiplied by r, it becomes ar, and ar is multiplied by r, it becomes ar square, and it goes ar cube. So if we add all these terms, we get a series. If we try to add all these terms, we try to get a series. This is the general form of the geometric series. So we can simply, in a compact form, we represent it like this: a into r to the power of n, where n goes from 0 to infinity. So here a is called initial term, and r is called common ratio. Okay, this is the general form of that geometric series. In the last video, we have seen one of the examples, like summation the series 1 by 2 to the power of n, where n goes from where 1 to infinity, it doesn't matter, 2 to 0 to infinity, whatever it is. And as an example, you can make this one 3 to the power of 1 by 3 to the power of n, and so on, or other 52 summation 52 by 5 to the power of 2n, where n goes to 1 to infinity. So these are some of the examples of the geometric series. Now we see how to solve this geometric series. Okay, I will give you a brief, like a theorem. I will give you a brief one. The geometric series summation a r to the power of n goes from 0 to infinity is convergent if modulus of r is less than 1, and divergent if modulus of r is greater than or equals to 1. Okay, so modulus of r is less than 1, which implies that r, the absolute value of r is less than 1. That means if we take away this, means r is in between 1 and -1, and if r is greater than, modulus of r is greater than or equals to 1, means if r is any other value than between minus 1 and 1. That means R belongs to minus infinity and minus 1 union 1 to infinity. If R is like this, then the geometric series does not converge there. So this is the statement. Now we have to prove the statement here. Let's see if it is convergent, and later we discuss if it is convergent. We said it is convergent. It is convergent to what number? We will also see that. For now we try to prove this statement, the theorem statement. So we may take the help of sequence of partial sums. So let's say the given geometric series is a r to the power of n and goes from 0 to infinity, and its corresponding sequence of partial sums, let's take it is Sn, where Sn, the sequence of up to, this is a summation of in this series up to the nth term. So it looks like ar plus ar square and so on up to ar to the power of n minus 1. So this is the sequence of the nth term in the sequence of its partial sums. We try to find what is the nth term, and then we try to find its limits and so on. So this is the nth term here. So this nth term looks like a 1 plus r plus, this one we take a as a we factor out a, then we get something like this, r square plus and so on, r to the power of n minus 1. Okay, now this is our Sn. Now we multiply this one, this Sn, the both sides of equation by 1 minus r. So we get a into 1 minus r, 1 plus r square and so on, r to the power of n minus 1. Now we see a, now we multiply these two. Now we multiply these two factors. If one is multiplied this factor, then we get the same factor, 1 plus r square plus and so on plus r to the power of n minus 1. Now if we multiply this factor with a minus r, what we will get? Minus r into 1 is minus r into r is minus r square, and minus and so on, minus r to the power of n minus 1 minus r is multiplied with the r to the power of n minus 1, we get minus r to the power of n. So these summations got, see, if these two get cancelled out, becomes 0 and so on up to here. So what we are left with is a into 1 minus r to the power of n. So this is our 1 minus r into Sn. So our Sn is, from this we form the Sn as a into 1 minus r, a into 1 minus r to the power of n divided by 1 minus r. So that is our Sn, that nth term in the sequence of its partial sums of the geometric series. Now we investigate this Sn, whether it converges or diverges as n tends to infinity for the different r and different a's. We will take the, what is the, all the possible combinations here. So what do we got here? Our Sn is a into 1 minus r to the power of n divided by 1 minus r. See here, this is our Sn. Now as n tends to okay, now we see that if our common ratio is, let's say, is 0, okay, is in between 1 and 0, okay, so then if we take the power, if we raise its power, a constant within 1 and 0, if we raise its power continuously, then it tends to 0 as n tends to infinity. Similarly, if r is 0, then anyways the geometric series itself becomes 0 after the first term. Okay, so no need to concern about that. Anyway, it's convergent. If r is less than 0 and greater than -1, then that means it is a constant between 0 and -1. So even this one also tends to 0 as n tends to infinity. For suppose, I will explain this statement using an example. So for suppose, if our r is -1/2, this is in between -1 and 0, so we can take this value for the r. If we raise its power, so -1/2 -1/2 whole square minus 1/2 whole cube minus 1/2 whole to the power of 4 and so on. So this is nothing but -1/2, this is nothing but 1/4, this is -1/8, this is 1/16. Okay, so it is oscillating between positive and negative, but evidently you can see that denominator is increasing. You can see that these denominators are increasing and so on. So this negative, and as it goes on, it approaches to the value 0. That's how it happens. And if our r, if this is the, what do you say, that this is the first case of the statement, and now we investigate the second case of the statement. If our r is 1, okay, the geometric series is a r to the power of n 0 to infinity becomes summation of nothing but a. If a is not 0, then if a is greater than 0, then the series converges to infinity, diverges to infinity. If a is less than 0, that means we are adding infinite number of a's, it diverges to infinity. If a is less than 0, we are adding infinite number of a's, so it diverges to negative infinity. That's if our r is -1, then we have a into -1 to the power of n, so 0 to infinity. Okay, so we see here this series is like okay, if we expand this, one, we get a plus negative a plus a plus negative a plus a. We can investigate this using the sequence of partial sums, but by now you must be capable enough to see this is a oscillatory sequence, because the first term is a, the sequence of partial sums behaves like this. So s1 is a, S2 is 0, adding up two terms. S3 is A, S4 is also 0, so it is oscillating between A and 0, oscillating between these two values. So we can say that this series is oscillating. Okay, when R is -1, the series is oscillating. If R is greater than 1, then take the Sn now, the sequence of partial sums here. Sn is A into 1 minus R to the power of n divided by 1 minus R. You see this one? Here R is greater than 1. If we raise its power to up to the raise, continuously raising 1, 2, 3 and so on along the integers, then this value would be raising so much. So we can say that this tends to positive infinity, since there is if R is greater than 1, since this is negative, we can see that 1 minus negative, this one tends to negative infinity by -1. We can see that it is converges to the infinity. Or you can write down this one like this: A into R to the power of n minus 1 by R minus 1. You can write like this also. In this way, it is clear that it is tending to infinity if R is greater than 1. Similarly, if R is less than -1, Sn is A into 1 minus R to the power of n by 1 minus R. We see here R is -1, so even this value is, we can say that the sequence of partial sums is oscillatory, because if n is positive here, R is positive, we get the negative okay, we get the positive value. Let's say if R is -1, okay, we examine this one very carefully. So if R is less than -1, for example, the Sn is given as A into 1 minus R to the power of n divided by 1 minus R. So let's take R is -2. Okay, we raise to for the first power, Sn becomes, if n is 1, that is S1, that's nothing but A will come. For suppose S3, this is A into 1 minus -2 to power 3 divided by 1 minus -2. So this is A into 1 minus, this is -8, -2 whole cube, this is -8, that is +8 divided by 1 plus 2. So this is positive, and let's say S4 is A into 1 minus, we can say -2 to the power of 4, that will be positive 1 minus 16 by 1 minus of -2. So this will be A into -15 divided by 3. Okay, so this is a negative, so it oscillates between positive and negative, and it increases as n increases. So we can say that the sequence, the geometric this sequence is oscillates infinitely, oscillates infinitely. So does the series, geometric series AR to the power of n. Okay, here we are least concerned about the initial term. We are most concerned about the common ratio here. So by the generalization, now we see the, now we summarize that we gathered the information here. Now up to now the all cases are over. So now we see, for suppose we take the real line here, this is the value 0 and this is the value 1 and this is the value -1, okay, and so on. For suppose if our r is in between -1 and 1, so it converges up to here, okay. If it is greater, if it is 1, diverges at a r is equals to, we can say that this is r line, okay, diverges, and if r is greater than 1, it is diverges, this one is diverges. If r is -1, if r is -1, then that is, if r is -1, that is oscillates here, when r is -1, oscillates finitely. If r is less than -1, then it oscillates infinitely, okay. So now I try to amend the statement that I given before, that in a geometric series a r to the power of n, if modulus of r is less than 1, the geometric series is convergent. And we cannot say here if r, previous statement, if r is greater than or equals to 1, I said it is divergent. No, we must say that it is not convergent. For particularly if r is greater than or equals to 1, for the particular cases, if r is greater than or equals to 1, we say that the sequence diverges. If r is equals to -1, the sequence oscillates finitely, and if r is less than -1, the sequence oscillates infinitely. So these are all the possible cases for the geometric series. Now we examine its convergence, okay. If it is converged, what is its value, what is the value that it is converging to? For suppose the sequence, the series a r to the power of the geometric series here, if r modulus of r is less than 1, that we know that it is convergent, and you can see that yes, the sequence of partial sums is a into 1 minus r to the power of n divided by 1 minus r. So as n tends to infinity, if modulus of r is less than 1, this term is going to be 0 as n tends to infinity. So we are left with a into, as n tends to infinity, that means limit n tends to infinity, Sn becomes, so this term becomes 0, so we are left with a by 1 minus r, okay. So this is the value that we are looking for here. This is the converging value. So the entire geometric series is converging to this one. If our common ratio modulus of r less than 1, then the entire geometric series a r to the power of n goes to 0 infinity is a by 1 minus r, okay. So for in the last section, in the last video, that we see as an example that the summation 1 by 2 whole to the power of n, where n goes to 0 to infinity. Here a is 1, r is 1 by 2, so we can say that a is 1, r is 1 by 2, this is 1 by 2, this is converging to 2. Similarly, if we say that 1 by 5 to the power of n, where n goes to 1 to infinity, you need to see this carefully, that n goes from 1 to infinity. I gave this one particularly, so the series will be like this: 1 by 5 plus 1 by 5 square plus 1 by 5 cube plus and so on. Here this is the a here, initial term, and r is also 1 by 5, because the initial term is multiplied by r, then we get 1 by 5 square, so we get the answer as 1 by 5 divided by 1 minus r, that is 1 by 5. So 1 by 5 divided by 4 by 5, 1 by 4. So this is the, what do you say, that converging limit of that convergent series. Now the application of this one is quite fascinating here, the application of the geometric series. Now we see the application here. Let's take one example to explain that. For suppose if we want to convert this 3.26 bar in terms of p by q, in terms of rational numbers form, how do we do this? See here, 3.26 bar is upon the 26, that means the number is like 3.26, 26, 26, 26 and so on. It goes, the 26 is repeated there, so we see that this one 3 plus 0.26, 26, 26, 26, we can write like this, and this 26 point, this first 26 is can be written like this: 26 by 100, it is nothing but 0.26. okay, for the simplicity purpose I will try to explain this one by adding one more step: 3 plus 0.26 plus 0.0026 plus 0.4026 and so on. Okay, this 3 plus 0.26 is nothing but 26 by 10 square, that is 100. This is 26 by 10 to the power of 4, that's 10,000. This is 26 by 10 to the power of 6 and so on. So here this part of the number is in the geometric series. Okay, geometric series. Now here the constant ratio from this to this one, we can see that it is 1 by 10 square is a constant ratio, so which is less than 1. Okay, so now this, we know that this is convergent and it is converging to a by 1 minus r. Here our a is 26 divided by 10 square, this is our initial term for this series. Okay, 3 plus is there, we are trying to find the sum of all the terms in the series. A by 1 minus our r is 10 square, so this is nothing but 3 plus 26 by 10 square, and now it is 10 square minus 1, that is 99. 100 minus 1, 99 by 10 square, so this is 3 plus 26 by 99, so it is 297, 323, that becomes 323 by 99. Okay, Hmm. That's how we find its value using the geometric series application. Now similarly we are to find, for suppose we are about to find 5.4 bar. This number, this is like 5.4. Okay, we take some other complicated one, not as simple as this. 5.23 bar is only for 3, so we have the number 23333 and so on. Okay, so this one is 5 plus 0.2 plus 0.03 plus 0.003 plus and so on. So now this is 3 by 100, 3 by 1000, 3 by 10,000 and so on. So this is in the geometric series. Now we try to simplify this one, because we know that this is convergent because the constant ratio is 1 by 10. This is infinite, that is the geometric series with the r is equals to 1 by 10, which is convergent. So we take the initial term 3 by 100 by 1 minus r, that is 10. So this becomes 3 by 100 divided by 9 by 10. So it becomes 3 by 90. Okay, so the answer will be 5 plus 2 by 10 plus 3 by 90. So 0.2 here is expressed as 2 by 10. So we take the LCM for all this. This is 450 plus 18 plus 3, 468 plus 3, 468 plus 3, that is 471 by 90. This is how we simplify this. This is a number of recurring number. We say that this is a decimal number which is recurring. So any recurring decimal number can be put in the form of p by q using this procedure. Okay, this is the very good application for the geometric series there. With this I will try to stop here. In the next video we'll see that what is the harmonic series and hyperharmonic series. Okay, this is one of the important form of the series that we learn in the basic level. Okay, that is enough for you. By the next class we will see those two series. For the homework, as a homework you can practice that not exercise, you can say that this is the whole, let's take, this is the summation minus 5 by 2 whole to the, not minus 5 by 2, not whole, minus 5 by 2 to the power of m. Check which of the series, state the nature of the series. 5 by 2 to the power of n minus 5 to the power of n divided by 2, and for all of them it goes from 0 to infinity. You can take this 0 to infinity for all the series. check whether which of the series is convergent in state its nature. If it is divergent, specify it is divergent to plus infinity or negative infinity. If it is convergent, specify the converging point. And if it is oscillatory, specify its oscillation, whether it is finite and infinite. And now express this 5.27 bar in the form of P by Q, and 5.312 we have the bar for 1 2. Okay, express these two in the P by Q form. As you take this as a homework. We stop here. See you, Tony.